Is it possible that the deepest acts of creation in our universe are born from the most profound moments of destruction? We look out into the cosmos and see nurseries of light, stellar forges where gas and dust are compressed into incandescent suns, birthing entire families of worlds from their leftover chaos. We see life, we see order, we see a patient architectural grandeur that spans billions of years. But this magnificent story of creation has a shadow, a dark reflection that is just as fundamental yet infinitely more terrifying. For every star that gives life, there is a star that will in its final desperate moments take it all away. And not just from a distance with the cold indifference of a dying ember, but through a final, horrifying act of consumption, an act of cosmic cannibalism. Imagine a sun not unlike our own, but ancient, weary, its long and stable life drawing to a close. For eons it was a source of constancy, a gravitational anchor holding its children in a predictable, elegant dance. Its light and warmth painted their skies, nourished their atmospheres, and perhaps on one of them sparked the improbable chemistry of life. This star was a parent, a creator, its planets born from the very same swirling cloud of primordial matter that formed its own core. They are made of the same dust, the same elements forged in the hearts of an even older generation of stars. They are in the most literal sense its flesh and blood, its cosmic progeny. For billions of years, this celestial family existed in a state of equilibrium, a testament to the quiet, reliable physics that governs the heavens. But the universe does not permit eternal stability. The engine at the heart of this star, a fusion furnace that has burned for longer than our species has existed, is beginning to sputter. The hydrogen fuel that powered its youth is all but gone. In a desperate bid for survival, the star's core begins to fuse heavier elements, a violent, unstable process that marks the beginning of its end. The physics of this moment is a paradox of cosmic proportions. As the core collapses inward under its own immense gravity, a shockwave of energy pushes the star's outer layers outward in a final grandiose expansion. The gentle life-giving sphere begins to swell its colour, shifting from a friendly yellow-white to a deep blood orange, the colour of a dying ember magnified 1 billion times. It is becoming a red giant. This is not a gentle transformation. It is a metamorphosis into a monster. The star, once a distant, manageable source of light, is now expanding to fill its own solar system. It is no longer a nurturing parent, but a ravenous, bloated leviathan, its gravitational reach becoming a suffocating embrace. The carefully defined habitable zone, that thin, precious ribbon of space, where liquid water could exist, is now a memory. The zone itself is pushed outward, fleetingly warming distant frozen worlds, before the star's engorged surface rushes out to meet them. The family of planets that once orbited at a safe, respectful distance now find themselves skimming the very edge of their creator's expanding atmosphere, a tenuous layer of superheated plasma that crackles with stellar flares and unimaginable radiation. Their placid orbits have become a death spiral. For the innermost worlds, the end comes swiftly. Any small rocky planets analogous to our own Mercury or Venus are the first to be sacrificed. They are consumed without ceremony, their solid bodies vaporized in an instant, their constituent atoms reabsorbed into the stellar furnace that first forged them. They become little more than a brief, almost imperceptible flicker in the star's luminosity, a final, silent gasp before being erased from cosmic history. But what of the larger worlds, the more distant children? What is their fate as this celestial blowtorch expands to claim its entire domain? What happens when a world with its own history, its own magnificent geology, perhaps even its own epic story of life faces its progenitor now turned executioner? This is a scene that until now has lived only in the realm of theory, a chilling footnote in the life cycle of stars played out in the silent logic of our supercomputer simulations. We have predicted it. We have modelled it. We have written equations to describe the unimaginable tidal forces that would tear a planet apart piece by piece as it plunges into its sun. We imagined the atmosphere being siphoned away, first a ghostly plume of gas pulled into a spiralling vortex, feeding the very star that is destroying it. We theorized about the planet's gravitational field fighting back a futile struggle against a force millions of times more powerful. We calculated the point at which the star's gravity would become so brutally asymmetric that it would stretch the world, pulling harder on its near side than its far side, elongating its solid sphere into a grotesque teardrop shape. This process, known with chillingly sterile accuracy as Roche-Lobe overflow, is the cosmic equivalent of being stretched on a rack. The planet's own gravity, the very force that held it together for billions of years, is overwhelmed. Rock and iron, once compressed into a solid core, would begin to flow like liquid, the world's surface cracking and melting under the dual assault of tidal stress and searing heat. It would scream, not with sound, for there is no air to carry it, but with gravitational waves, ripples in the fabric of space-time, and with a final, spectacular burst of light as its matter collides with the star's surface. This is the death of a world. Not a quiet fading, but a violent, spectacular dissolution. An obliteration so complete that future alien astronomers studying this star a million years from now might find no evidence that this planet ever existed at all, save for a subtle, almost imperceptible contamination of heavy elements in the star's atmosphere, the ghost of a consumed child. For all of human history, this cosmic horror story was just that, a story. A campfire tale told by astrophysicists. We knew it had to happen. The laws of physics demanded it. Across the billions of stars in our own galaxy, this exact tragedy must play out thousands of times every single year. It is a fundamental routine part of the universe's cycle of death and rebirth. Yet seeing it was another matter entirely. The universe is vast and stars are blindingly bright, their glare easily hiding the final intimate moments of the planets caught in their gravitational maw. To witness this event, to actually capture the light from a planet's final hour, was considered a near impossibility, a stroke of astronomical luck so profound it was barely worth hoping for. But we are living in a new age of discovery. Our eyes on the sky are no longer just mirrors and lenses. They are sophisticated digital sentinels capable of measuring the universe with a precision that was once the stuff of science fiction. We can now detect the subtle dimming of a star as a planet passes in front of it, even from hundreds of light years away. We can analyze the chemical composition of starlight, reading the atmospheric signatures of worlds we will never visit. We have built instruments so stable, so sensitive that they can perceive the universe not just as a static photograph, but as a living, breathing, evolving entity. We have, in essence, built a time machine that looks not into the past, but into the future. And with these new eyes, we went looking for the ghost. We went hunting for the evidence of this ultimate cosmic crime, and then we found it. Not an echo, not a chemical ghost, not a simulation running on a bank of computers. We found a star in the very act of devouring one of its own planets, and we captured it. Not as a single blurry data point, but in breathtaking high-resolution detail. The title of our story, A Star That Eats Planets Caught in 4K, is not hyperbole. It is a declaration of a new reality. We have a front row seat to one of the most violent and fundamental processes in the cosmos, a spectacle of creation and destruction, unfolding before our very instruments. The data that poured in was more than just numbers on a screen. It was a film, a recording of a world's final agonizing moments written in the language of light. This unprecedented observation forces us to move beyond theory and confront the raw, terrifying reality. What does it truly look like when a star's atmosphere, thin but unimaginably hot, first makes contact with a planet's magnetic field? What is the signature of a world's crust and mantle being stripped away layer by layer and funneled into a stellar furnace? Does the planet's core survive the initial plunge, or is it too disintegrated into a rain of molten iron and nickel? These are the questions that have haunted astronomers for decades, and for the first time we have the chance to answer them. We are no longer guessing. We are watching. We are witnessing the autopsy of a world performed in the real time by the very star that killed it. But the importance of this discovery extends far beyond mere cosmic curiosity. This is not just the story of a distant anonymous star system. It is a preview, a dress rehearsal for the final act of our very own solar system. Our sun too is aging. It too is burning through its hydrogen fuel. In about 5 billion years, it will begin its own monstrous expansion its own transformation into a red giant. Its outer edges will swell past the orbit of Mercury, vaporizing it instantly. It will consume Venus, boiling its sulfuric acid atmosphere and melting its rocky surface into a slag heap before swallowing it whole, and then it will come for us. The Earth, our fragile blue oasis, will face its creator. The oceans that harbour life will boil away, steaming into a thick, choking atmosphere that will then be stripped from the planet by the solar wind. The continents will glow red hot, the very rock of our planet's crust beginning to melt. Whether the Earth is completely engulfed by the sun or left as a charred, tidally locked cinder, orbiting a dying star is a matter of intense scientific debate. But our ultimate fate is sealed. The end of our world will not come from an asteroid or a plague or our own folly. It will come from the very star that has nurtured us for 4.5 billion years. The giver of life will become the agent of our annihilation. The event we have now captured, this distant planetary death, is therefore more than just a scientific breakthrough. It is a message in a bottle sent to us not across space but across time. It is a glimpse into the deep future, a chillingly accurate portrait of Earth's final day. By studying this star and the planet it is consuming, we are studying ourselves. We are learning about the precise mechanics of our own inevitable end. The light from this dying world travelled for hundreds of years to reach our telescopes, arriving just in time for us to have built the technology capable of understanding its final desperate testament. This is not a story of endings, but of understanding. Every element in your body, the carbon in your cells, the calcium in your bones, the iron in your blood was forged in the heart of a star that lived and died long before our sun was born. We are all of us made of stardust. The universe recycles everything. The material of this consumed planet will be enriched with new elements inside its star, and when that star finally dies, it will cast those elements back out into the void, seeding the next generation of stars and planets. The death of this one world may well be the building block for thousands of new ones. Destruction and creation locked in an eternal cosmic dance. So we invite you to join us on a journey to the edge of existence, to witness an event of unimaginable scale and violence captured with a clarity we once thought impossible. We will peel back the glare of a star and reveal the final moments of a world caught in a gravitational tide. We will analyse its light, decode its chemistry, and listen to its silent gravitational scream. This is not just a documentary about astronomy. It is a story about legacy, about inheritance, and about the beautiful, terrifying, and inescapable connection between a star and its planets. We have the footage, we have the data. The story of a star that eats its young is about to begin. Every second of every day a clock is ticking deep within the heart of our sun. It is a thermonuclear timepiece counting down not in minutes or hours but in billions of years. Its steady rhythm has governed the history of our world, nurturing life from the primordial oceans. But this clock is not eternal. It is counting down to a final spectacular moment, a prophecy written in the laws of physics. A day when our life-giving star will swell into a monstrous world, devouring giant, its fiery breath reaching out to consume Mercury, then Venus, and perhaps finally our own home. This is not science fiction. This is our planet's ultimate destiny, a fate shared by countless worlds across the uncounted galaxies. For generations, this cosmic drama has played out only in the silent mathematics of our supercomputers and the vivid landscapes of our imagination. We've known the story's ending, but we've been forced to read it from a distance like an ancient myth. We have never had a front row seat. We have never seen the final act. We have never until now witnessed the murder of a world in real time, capturing its final moments in the cold, unblinking eye of a telescope. The story of how we finally caught a star in the act is a tale of patience, of technological audacity, and of our unyielding desire to see the universe for what it truly is, a place of both breathtaking creation and terrifying destruction. To understand the crime, you must first understand the culprit. A star like our sun is not a static object. It is a living, breathing entity locked in a monumental battle with its own gravity. For billions of years it maintains a delicate, life-sustaining equilibrium. Deep within its core, a region of unimaginable pressure and heat, the star acts as a cosmic furnace. It fuses hydrogen atoms into helium, releasing a torrent of energy in the process. This outward push of radiation pressure is what holds the star up, a constant photonic wind fighting against the relentless inward crush of its own immense mass. For eons this balance holds. The star shines with a steady, predictable light, a reliable anchor in its planetary system. But the fuel for this celestial engine is finite. Every moment the star burns through its vast reserves of hydrogen, and like any fire it must eventually begin to run low. What happens next is not a gentle fading into the night. It is a violent transformative convulsion, a spectacular metamorphosis that turns the giver of life into an all-consuming monster. The process begins in silence deep in the stellar core. Over billions of years, the hydrogen fusion creates a byproduct, a kind of thermonuclear ash helium. Being heavier than hydrogen, this helium ash sinks to the very centre of the star, accumulating into a dense inert ball. For a time, this doesn't change much. A shell of hydrogen continues to burn around this growing helium core, but eventually a critical tipping point is reached. The hydrogen fuel in the core is exhausted. With the furnace at its heart sputtering out, the outward radiation pressure plummets. Gravity, the star's eternal foe, begins to win. The helium core, now deprived of the force holding it up, collapses catastrophically under its own weight. This collapse is the trigger for the star's dramatic second act. As the core compresses, its temperature and pressure skyrocket to levels previously unimaginable, reaching hundreds of millions of degrees. While the core itself is no longer fusing, this incredible new heat source begins to furiously ignite the surrounding shell of hydrogen, causing it to burn at a vastly accelerated, desperate rate. This runaway fusion in the shell unleashes a flood of energy so immense that it completely overwhelms the star's gravitational grip on its outer layers. The surface begins to expand, to swell, to billow outwards like a celestial tide of fire. The star we once knew, the familiar yellow-white dwarf, begins its transformation into a red giant. Its surface temperature actually cools as it expands over a much larger area, causing its colour to shift from brilliant white to a deep, menacing crimson. But its total luminosity, the sheer amount of energy it pours into space, increases 100, even 1,000-fold. It becomes a bloated, terrifying version of its former self, its gaseous tendrils now stretching millions upon millions of kilometres further into space than ever before. For any planets unlucky enough to be orbiting in the star's inner sanctum, this expansion is a death sentence delivered in slow motion. The heavens themselves begin to close in. The familiar pinpoint of their sun grows in the sky first into a disk, then a terrifying world-filling wall of fire. The end is coming, and it is a multi-stage process of planetary annihilation. First comes the inferno. As the star's surface creeps closer, the planet is subjected to a celestial blowtorch. Its surface temperature soars, boiling away, oceans, searing continents, and incinerating any trace of an atmosphere. The planet becomes a scorched, airless cinder, its day side a permanent landscape of molten rock. But this is just the prelude. The true destruction is delivered by the star's expanding outer layers, a tenuous but inescapable wave of superheated gas. The planet's orbit, once a stable path through the vacuum of space, is now a death spiral through the star's own atmosphere. It begins to experience drag, a cosmic friction that bleeds away its orbital energy. With every pass, its trajectory decays, pulling it ever closer to the churning stellar furnace below. It is a moth being drawn inexorably into a cosmic flame, its fate sealed. As it plunges deeper, another more primal force takes hold: tides. We think of tides as the gentle rise and fall of our oceans, but near a star they become instruments of gravitational torture. The star's immense gravity pulls more strongly on the near side of the planet than the far side. This differential force begins to stretch the world, deforming it from a sphere into an elongated, egg-like shape. The planet is being pulled apart. Its rocky mantle cracks, its iron core groans under the strain. If the planet is massive enough, it might even trigger a spectacular response from the star itself. Its gravitational influence can dredge up material from the star's deeper layers, causing the star to spin faster and brighten even more, a final violent conversation between a dying world and its devourer. Eventually the planet reaches a point of no return known as the Roche limit. Here, the tidal forces exerted by the star become stronger than the planet's own gravity holding it together. The world dissolves. It is shredded into a stream of molten rock and superheated gas, a glowing ribbon of its own remains that wrap around the star in a fiery embrace. This debris then rains down onto the stellar surface, creating a spectacular transient outburst, a flash of light and heat that marks the planet's final desperate scream. The star for a brief moment brightens and bloats, appearing to burp as it digests its own child, and then silence. The star settles, the light fades, and the only evidence that a world ever existed is a subtle chemical contamination in the star's atmosphere, a ghostly fingerprint of the elements it has just consumed. For astronomers, this entire sequence was a cornerstone of stellar theory, a fundamental chapter in the cosmic story. Yet it remained exactly that, a story, a magnificent, well-supported but ultimately unproven theory. Witnessing it directly was considered a challenge of almost insurmountable proportions. The universe, after all, does not perform on command. The first great hurdle is scale. Our Milky Way galaxy is a city of over 200 billion stars spread across 100,000 light-years. Finding a single star in the precise fleeting moment of consuming a planet is like trying to find one specific firefly blinking in a continent-spanning forest at night during a storm. The events are, from our perspective, impossibly remote and infinitesimally small. Even if you happen to be looking at the right star at the right time, the event itself is cosmically brief. While the red giant phase lasts for millions of years, the final dramatic plunge of a planet is thought to take place over mere months or even weeks. In the grand timeline of the universe, it is less than the blink of an eye. You could stare at a star for 100 years and see nothing only for it to swallow its planet in the 1 year you decided to look away. This cosmic game of hide-and-seek was made even harder by the nature of the event itself. The death of a planet is not a clean affair. The process kicks up an enormous amount of dust. As the planet is vaporized and its material is ejected, it can create a thick obscuring shroud around the star, a cosmic smokescreen that hides the very crime we wish to see. This dust cloud blocks visible light, meaning that just as the main event is happening, the star can paradoxically appear to dim from our point of view. We would be staring directly at the scene yet be blinded by the celestial debris. For decades, astronomers were relegated to the role of cosmic forensic scientists, searching not for the act itself but for the circumstantial evidence left behind long after the fact. They became hunters of stellar ghosts. One of the most tantalizing clues was a chemical anomaly involving the element lithium. Stars like our Sun are very efficient at destroying lithium, burning it up in their hot interiors. Finding a red giant that was unusually rich in lithium was therefore a major red flag. The leading theory was that the star had recently ingested a planet, and the lithium we were seeing was the undigested chemical remains of that world, temporarily enriching the star's surface before it too was destroyed. This was a clever piece of detective work, but it was indirect. It was like finding a suspect with a smoking gun, but with no body and no witnesses. The lithium could perhaps be explained by other more complex stellar processes. Another line of inquiry involved looking for red giants that were spinning unusually fast. The thinking was that as a planet spiraled inwards, it would transfer its orbital momentum to the star like a figure skater pulling in their arms to spin faster. A rapidly rotating red giant might be a star still reeling from a planetary meal. But again, this was circumstantial. Stellar rotation is a complex phenomenon, and other mechanisms could potentially spin up an old star. The community was divided. These smoking guns were tantalizing, but they were not definitive proof. A deep-seated skepticism remained about our ability to ever truly catch the event in flagrante delicto. The idea of not just detecting a subtle chemical trace, but of capturing the entire light show, the initial brightening, the dust-induced dimming, the final infrared flare-up from the heated debris seemed like a fantasy. It would require a fundamentally new way of watching the sky. We could no longer afford to be cosmic snipers pointing our powerful telescopes at one target at a time hoping to get lucky. The old methods were like trying to photograph a bolt of lightning by pointing a camera at a tiny patch of a thundercloud. What we needed was a camera that could see the entire storm at once. We needed to replace the sniper rifle with a vast, unblinking surveillance network. And in the early 21st century, that is precisely what we built. a new generation of robotic observatories began to scan the heavens with an unprecedented hunger for data. Projects like the Zwicky Transient Facility, or ZTF, were designed not to take deep, beautiful portraits of distant galaxies, but to do something much more dynamic. They patrol the entire night sky every few days, taking snapshot after snapshot of millions of stars. Their powerful software then acts as a celestial security guard, comparing each new image to the previous one, looking for anything that has changed. A star that has suddenly brightened, a supernova that has just exploded, an asteroid streaking across the field of view. They are change detection machines built to catch the universe in the act. This relentless, high-cadence monitoring of the sky was the first crucial piece of the puzzle. It gave us a chance to spot the initial flash, the scream of a planet beginning its final plunge. But seeing that flash in visible light was only part of the story. To pierce the dusty veil thrown up by the event, we needed to see in ways our eyes cannot. We needed infrared vision. Telescopes like NASA's Neowise satellite provided this crucial capability. Orbiting above our obscuring atmosphere, it scanned the sky in infrared wavelengths which can pass through clouds of dust that are opaque to visible light. Where a telescope on Earth might see a star suddenly dim as it creates its dusty shroud, an infrared observatory would see the opposite, a sudden brilliant flare as that very same dust heated by the star began to glow with thermal energy. By combining the all-sky rapid-fire alerts from ground-based surveys with the dust-piercing vision of space-based infrared telescopes, a new strategy emerged. We could finally triangulate the event. We could see the initial flash of the impact, watch the star mysteriously disappear in visible light, and then confirm our suspicions as it blazed back to life in the infrared. This wasn't just about getting a blurry picture. The goal was to capture the event in what we might call 4K, not in terms of spatial resolution, but in terms of data richness. By measuring the precise changes in the star's brightness over time, its light curve, we could model the size and speed of the impact. By breaking the star's light into its constituent colours, its spectrum, we could analyse the chemical composition of the debris cloud, performing a celestial autopsy on the planet from light years away. We could weigh the victim and determine what it was made of. The tools were finally in place. The theoretical groundwork had been laid over a century of stellar physics. The skepticism born from decades of fruitless searching was giving way to a new cautious optimism. The stage was set for one of the most dramatic and long-sought observations in modern astronomy. All that was needed was for a single distant star among the billions to finally reveal its terrible secret to our waiting eyes. The hunt for the ghost in the machine was over. It was time to catch the monster itself. And so the gauntlet was thrown down. The theory was no longer a gentle abstraction, a neat equation on a chalkboard. It was a cosmic dare. The universe was hiding its crimes in plain sight, and for generations we had lacked the means to even file a report. To catch a star in the act of planetary consumption required a radical shift in perspective, a move away from simply capturing the light of distant suns and towards the far more intricate art of interrogating it. For us to bear witness, we had to stop being photographers of the cosmos and become its forensic investigators. The light travelling for centuries, even millennia, to reach our telescopes wasn't just a picture. It was a message, a story encoded in a language of photons. The challenge was to build the universal translator, a key to unlock the chemical secrets whispered across the void. The solution, forged in cryogenically cooled chambers and polished to near-atomic perfection, would be an instrument of breathtaking sensitivity. It was the rise of the stellar spectrograph, our prism to the soul of a star. You see, for most of astronomical history, a star was a point of light, its story told in brightness and position. But locked within that simple gleam is a spectrum, a rainbow of information. When you pass starlight through a prism, or more precisely a diffraction grating it, unfurls into its constituent colours. But this stellar rainbow is flawed, scarred with thin, dark lines. These are absorption lines, and each one is a chemical fingerprint, the unambiguous signature of a specific element in the star's atmosphere, absorbing certain wavelengths of light. It's how we know the sun is made of hydrogen and helium, and how we can read the chemical sensors of a galaxy a billion light-years away. For our purposes, however, We needed to go beyond a simple census. We needed to detect a change, a fleeting addition to the star's atmosphere so subtle it would be like trying to hear a single pin drop in the middle of a hurricane. The existing tools were simply not up to the task. Their vision was too blurry, their hearing too dull. We needed a new generation of eyes. Enter the Titans. High in the barren stillness of the Atacama Desert, or perched on the sacred peaks of Mauna Kea, colossal new observatories were stirring. These were not just telescopes. They were technological cathedrals, their domes sliding open like eyelids to the heavens. And deep within their metallic hearts, nestled in vacuum-sealed, temperature-controlled chambers, were the instruments that would change everything. Spectrographs with names like HARPS, Espresso, and HIAS. These weren't just prisms. They were celestial polygraphs, masterpieces of engineering designed for one purpose: to achieve unprecedented stability and resolution. Imagine a machine so sensitive that the heat from a single human hand standing meters away could ruin an entire night of observations. A device so precise it could detect a wobble in a star's motion, caused by an orbiting planet, a motion equivalent to a slow walk from hundreds of light-years away. This was the level of precision required. These spectrographs were miracles of stability. To dissect the light with the required finesse, the instrument itself had to be a fixed, unmoving anchor in a world of variables. They were housed in chambers where the temperature was controlled to within 1,000th of a degree Celsius. The pressure was kept as constant as a law of physics. This created a pristine, unchanging environment, ensuring that any variation detected in the starlight was genuinely from the star itself, and not some artifact of our own turbulent world. The light collected by an 8 or 10 meter primary mirror, a vast, shimmering pool of silvered glass, was funneled through a gossamer-thin optical fibre, a crystalline nerve cell connecting the telescope to the spectrograph's brain. Inside, the light would be bounced, split and stretched across a vast detector, its spectrum unfurled to a length of several meters, revealing those dark absorption lines with a clarity never before seen. We could now not only see the fingerprints, but we could also check for smudges. This technological leap was matched by a human one. The quest attracted a new breed of astronomer, part physicist, part data scientist, part cosmic detective. These weren't solitary figures in lonely domes. They were global teams connected by high-speed networks working in a state of perpetual caffeinated motion. We follow one such group, a collaboration stretching from observatories in Chile to data centers in Germany. For them, the day never ended. As the sun set over the Andes and the telescope dome opened to the crystalline night, their colleagues in Europe were just waking up, ready to receive the flood of data. They were hunting for ghosts in the machine, for signals so faint they were buried deep within the noise of the universe and the instrument itself. Their target wasn't just any star. They were looking at mature, stable suns, stars like our own, which should have settled into a quiet middle age. In these stars, the heavier elements, the metals and rocks that form planets, should have long ago sunk beneath the turbulent surface, pulled down by gravity into the star's deep interior, hidden from our view. The atmosphere of a star like this should be pristine, a clean slate of mostly hydrogen and helium. Finding elements like lithium-ion aluminum or silicon floating on the surface would be deeply strange. It would be like finding a shipwreck on a mountain peak. These refractory elements, the very building blocks of terrestrial worlds, are heavy. They don't belong in the outer layers of a calm sun-like star. Lithium in particular is a crucial clue. It's a fragile element easily destroyed in the intense heat of a star's interior. A middle-aged star should have burned through nearly all of its initial supply. Therefore, a sudden, inexplicable abundance of lithium in a star's atmosphere could only mean one thing: it had been recently delivered. It was a chemical smoking gun, the indigestible remains of a recent meal. This was the signal they were looking for, the spectral scream of a planet being torn apart and consumed. The process was painstaking. For months, which bled into years, the team collected data on hundreds of candidate stars. Night after night, the telescopes would stare, gathering photons, building up a deep, detailed portrait of each target's chemical makeup. The data streamed across the globe, terabytes of information that had to be meticulously cleaned, calibrated, and analysed. An astronomer might spend an entire day processing the light from a single star captured over just a few hours. They developed sophisticated computer algorithms, complex filters designed to subtract the known signals, the star's own light, the faint glow of our own atmosphere, the electronic hum of the detector in the hopes of isolating the unknown. It was an exhaustive search for a single anomalous note in a cosmic symphony. They were listening for the whisper of a dying world. Then one morning it appeared. Buried in the data from a star designated AATC 739, a sun-like star some 500 light-years away, an analyst in Munich noticed something odd. It wasn't a dramatic flashing siren. It was a subtle warping of the baseline, a faint but persistent anomaly in the spectrum. When they zoomed in, their hearts began to pound. There it was, a faint but unmistakable absorption line for lithium stronger than it had any right to be, and it wasn't alone. Further analysis revealed traces of other telltale elements: iron, magnesium, silicon. The rocky stuff, the raw materials of a planet. The initial reaction was not celebration, but a deep professional skepticism. It was too perfect, too clean. In science, the first sign of a paradigm-shifting discovery is almost always assumed to be a mistake, an error in the calibration, a flaw in the detector, a bug in the code. They spent weeks trying to break their own discovery. They reran the analysis from scratch. They used different software, different calibration frames. They had colleagues at a competing observatory on a different continent use a different telescope to observe the same star, a crucial cross-check to rule out instrumental error. The signal remained. It was real. The star RZ739 was chemically peculiar. The news rippled through the team, a current of controlled excitement. They had it. The first concrete evidence, the chemical echo of a devoured world. They drafted the paper, their conclusions carefully worded but revolutionary. They had found the ghost at the feast. But as they prepared to share their findings with the world, the confrontation truly began not from without but from within the fiercely critical world of astrophysics itself. The moment their preliminary findings were discussed at a conference, the counter-arguments emerged. The scientific community, as it must, played the role of the ultimate devil's advocate. Is a planetary meal the only possible explanation? One prominent theorist proposed an alternative. What if the star hadn't eaten a full planet but had merely grazed the edge of a vast primordial asteroid belt? This could in theory dredge up a significant amount of rocky material polluting the star's atmosphere with the observed elements. It was a plausible scenario, difficult to rule out entirely. It would produce a similar chemical signature, though perhaps with a different distribution of elements. The debate intensified. How could you distinguish between the star consuming a single large planet versus a death by 1,000 cuts from a swarm of smaller bodies? The current data wasn't quite sharp enough to provide a definitive answer. The evidence was compelling but not yet conclusive. Then came another, even more challenging hypothesis. Perhaps this had nothing to do with external objects at all. Some stars are known to have powerful magnetic fields that can dredge up material from their own deep interiors, a process known as convective overshoot. Could a previously unknown form of stellar activity be churning the star's guts, bringing long-hidden heavy elements back to the surface? This would mimic the signature of accretion, perfectly creating a planetary ghost from the star's own internal machinations. The star wouldn't be a predator. It would just have a case of cosmic heartburn. This possibility was deeply unsettling to the Discovery team. It meant their smoking gun might have been fired by the victim itself. The confrontation was now a full-blown scientific impasse. The spectral lines were undeniable, but their origin was a maddening enigma wrapped in a mystery. The team was split. Younger members, confident in their data, pushed to publish their planetary consumption theory. Senior astronomers, scarred by past claims that were later retracted, urged caution. The tension was immense. Careers were on the line. To make such an extraordinary claim required more than just extraordinary evidence. It required unassailable proof, evidence that eliminated every other possibility. You can imagine the late-night arguments fueled by coffee and intellectual passion, the whiteboards covered in frantic equations and diagrams of stellar interiors. They were grappling with the very nature of scientific truth, Caught between the thrill of a profound discovery and the terrifying possibility of a colossal error, the ambiguity was the enemy. The faintness of the signal, the multiple plausible explanations, it all conspired to keep the truth just out of reach. This crucible of debate and doubt forced them to innovate once more. It was clear that simply detecting the presence of these elements was no longer enough. They needed more information. They needed to understand the timing, the sequence of events. Was this pollution a recent event, or had the star been simmering with these extra elements for millions of years? An ancient contamination wouldn't look the same as a fresh kill. A single, massive ingestion of a planet would dump a large, concentrated plume of material onto the star, which would then slowly mix and diffuse into the outer layers over thousands of years. In contrast, a steady rain of asteroids might produce a more constant low-level signature. The key was to find a way to date the event to establish a timeline for this cosmic crime scene. They realized the answer might lie not in the elements that were present, but in how they were distributed. They needed to move beyond traditional spectroscopy and pioneer a new technique, differential abundance analysis. They would meticulously measure the ratios of different elements to each other. The specific blend of materials in a rocky planet is distinct from the blend found in a star's deep interior, or in a swarm of primitive asteroids. By comparing the precise ratios of iron to magnesium or silicon to calcium in the star's atmosphere to the ratios we see in meteorites from our own solar system, they could potentially find a match. This was data analysis on an entirely new level of precision. It required developing new atmospheric models for stars, new algorithms capable of teasing apart spectral lines that were blended together, fighting for every last decimal point of accuracy. They went back to the data this time looking not for a single clue, but for a complex pattern, a coherent story told in the language of elemental ratios. It was like trying to reassemble a shattered vase from microscopic shards of dust. They needed more light, more observations not just of Rs 7 through to 9, but of dozens of similar stars to build a baseline to understand what normal truly looked like. The confrontation with their critics had pushed them into a corner, but it was in that corner that they found their path forward. They now had a new tool, a new question to ask the universe. The ambiguity that had stalled them had also given them a new weapon. They were no longer just looking for evidence of a meal, they were now looking for the recipe. As they began this new, more focused search, the entire field held its breath. The answer was waiting, hidden in the faint light of a distant anonymous star, promising to either confirm a discovery for the ages or send them back humbled to the drawing board. For weeks the vigil had been a study in cosmic patience. At the Atacama Large Millimeter Array, nestled high in the Chilean desert, a global team of astronomers had their instruments trained on a single, unassuming star, a yellow dwarf designated HD WST-368. They were watching for the subtle tremors in spacetime. We had just explored the faint gravitational whispers that might betray the dance of its inner worlds. The system was a known oddity, its planets locked in a precarious, chaotic ballet that models suggested could not last. They were hunting for the prelude to a catastrophe, expecting a slow, stately gravitational decay played out over millennia. They were entirely unprepared for the universe to pull back the curtain on the final violent act. It began not with a whisper, but with a sudden blinding scream of light. The alert systems programmed to flag minor stellar fluctuations blared to life with an intensity no one had ever witnessed from a star of this type. This wasn't the gentle rise and fall of a typical stellar flare, a localized magnetic eruption on the star's surface. This was a global conflagration. HD 1836508, a star that should have been entering a quiet middle age, suddenly brightened by nearly a full magnitude, a change so dramatic it would have been visible to the naked eye had anyone been standing on a world in a neighbouring system. The initial photometry data, the raw measure of brightness over time, painted a picture of pure chaos. It was a jagged, angry spike on a graph that for decades had been almost perfectly flat. The star was convulsing. But raw brightness was only the first clue in this rapidly unfolding celestial mystery. True understanding, the kind of high-definition clarity that separates observation from comprehension, requires breaking that light down into its constituent parts. This is the art of spectroscopy, the science of reading the chemical barcodes imprinted on starlight. As observatories around the world pivoted their mirrors in a frantic coordinated effort to catch this unprecedented event, the spectrographs began to tell an even more disturbing story. The light from HD 1836 Fussifers was being filtered through a cloud of vaporized material, and the barcodes they were reading were impossible. Think of a star's atmosphere as a library of elements, each with its own unique spectral signature. For a star like HD 1836 Fe8, that library should be well established, dominated by the primordial elements of hydrogen and helium, with trace amounts of heavier materials forged in its core. Yet as the data flooded in new forbidden volumes began appearing on the shelves, there was a sudden dramatic spike in lithium. This was the first profound impossibility. Lithium is like stellar kindling. A star of this age should have burned through its entire surface supply billions of years ago. Finding a massive plume of it now was like discovering a fresh unlit match in the heart of a settled bonfire. And it was not alone. Alongside the lithium came an unmistakable surge of silicon, magnesium and iron, a cocktail of heavy rocky elements that had no business being in the star's upper atmosphere. These are the very building blocks of terrestrial worlds, the stuff of planetary crusts and molten cores. In the cool outer layers of a star they should sink, pulled down by gravity into the searing furnace below, hidden forever from our view. To see them not just present but surging in vast quantities suggested that something dense, something rocky, and something enormous had been recently and violently delivered to the star's surface. The star wasn't just flaring, it was belching. It was showing the chemical ghosts of something it had just consumed. The team was in a state of controlled disbelief. The first instinct in science is always to suspect the instrument, then the observer, and only then the universe. Could it be a calibration error? A flaw in the detector? Was a cloud of interstellar dust passing between us and the star, contaminating the signal with its own elemental makeup? A frenzy of cross-checks began. Teams in Hawaii, Spain and Chile ran diagnostics comparing their readings. The signals were identical. They pointed their instruments at neighbouring stars to ensure their equipment was clean. The neighbouring stars looked perfectly normal. The ghost was not in their machines. It was 300 light-years away, swirling in the atmosphere of a dying star system. With every other conventional explanation systematically dismantled, they were left staring at the raw, unblinking data, a dataset of such unprecedented clarity, it would forever be the benchmark for this brand of cosmic violence. It was our first 4K view of a planetary execution. The light curve, that jagged spike of brightness, was not the chaotic signature of a stellar flare after all. When they modelled it with excruciating precision, they saw something else entirely. It was the signature of a massive object plunging through the star's outer layers. The initial smaller rise in brightness was the planet hitting the chromosphere, its atmosphere flash boiling into space. The colossal primary peak was the moment the main body, a world likely larger than Jupiter, disintegrated under the unimaginable tidal forces and temperatures, releasing a calamitous burst of energy. It was the death scream of a world translated into the language of light, and the fallout, the chemical debris, told the rest of the story. The models they ran were chillingly precise. The specific ratios of silicon to iron, the sheer quantity of vaporized rock, perfectly matched the predicted composition of one of the system's inner gas giants, a world they had named Persephone. They realized they weren't just seeing a star-eat Eeyore planet. They were seeing HD 1836 Fumfif8 eat its own child. The lithium was the final damning piece of evidence. While a star burns its own primordial lithium, a massive planet, particularly a gas giant, acts like a cosmic refrigerator. Its immense gravity and deep core can preserve that original lithium for eons. The sudden appearance of so much of it in the star's atmosphere was the planetary equivalent of a fingerprint, a unique chemical signature left at the scene of the crime. The star had swallowed the planet whole, and the planet's unburnt lithium was now spread across its killer's face for all the universe to see. This was no longer a theoretical model running on a supercomputer. It was not a statistical probability derived from studying stellar populations. This was a live feed. For the astronomers watching, the graphs and spectral lines on their screens transcended mere data. They became a visceral, real-time broadcast of a world's end. Each photon arriving at their detectors had travelled for 3 centuries, carrying with it the final incandescent moments of a planet's existence. They were watching a ghost, an event that had actually happened during the age of Galileo, but whose light was only now reaching us. The collective feeling in control rooms across the globe was not one of triumphant discovery, but of profound, sobering awe. They were cosmic archaeologists who had stumbled not upon a ruin, but upon the cataclysm that created it still in progress. The implications rippled outward, forcing a re-evaluation of everything we thought we knew about the stability of solar systems. We have a tendency to view our own cosmic neighbourhood as a paragon of celestial clockwork, a place of predictable orbits and stately reliable motion. But the gruesome end of Persephone served as a stark, terrifying reminder that the universe operates on its own often violent terms. The gravitational dance that holds systems together can with the slightest perturbation become a death spiral. Planets are not guaranteed their orbits for eternity. They are survivors clinging to a precarious gravitational ledge. HD 183658 showed us what happens when one of them loses its grip. This single explosive event transformed the field of stellar astronomy. What was once a hypothesis, a fringe theory about stellar pollution, was now an observed fact, captured with a clarity that was both beautiful and horrifying. The data was so complete, so unambiguous, that it became the Rosetta Stone for stellar ingestion. Now astronomers could look back at older, less complete data from other peculiar stars with similarly unexplainable chemical compositions and see the echoes of similar ancient tragedies. They now knew what to look for. They had the spectral fingerprints of a planetary ghost, the light curve of a final desperate plunge. HD 183658 had provided them with the anatomy of destruction, and for us the story becomes deeply personal. We look at this event, this star devouring its world, and we cannot help but see a dark reflection of our own potential fate. The same laws of physics that govern the orbits of Persephone govern the Earth. The same chaotic dynamics that sealed its doom are present in some small measure in every system across the galaxy, including our own. The death of this distant world was not just an astronomical curiosity, it was a cautionary tale written in fire across the cosmos. It was a confirmation that the heavens are not always serene, and that the very stars that give us life can also, in a moment of gravitational chaos, become the ultimate agents of annihilation. The evidence was now undeniable, the case was closed. But this shocking confirmation was only the turning point. It answered the question of if it happens, but in doing so it opened up a far more complex and disturbing series of questions about the very nature of stars themselves. For when a star consumes a world, it is not merely a destructive act. It is also an act of transformation. The star too is changed by the encounter, and the evidence suggests that these cataclysms might do more than just end worlds. They might, in some bizarre twist of cosmic alchemy, fundamentally alter the star's destiny and even pave the way for new creation from the ashes. The evidence was irrefutable, etched in the cold, hard language of light and time. The dip, the flare, the telltale chemical ghost in the star's spectrum, they all screamed a single terrible truth. We had borne witness to the consumption of a world. But to confirm an event is one thing, to truly comprehend it is another entirely. Now with the verdict delivered, we must step past the moment of discovery and descend into the mechanics of the cataclysm itself. We must follow the doomed planet on its final downward path, not as detached observers, but as forensic astronomers, piecing together the last moments of a world torn asunder by its own parent star. This is not a gentle fading into the night. It is a disassembly, a violent deconstruction, on a scale that challenges the very limits of our imagination, a process that begins not with fire but with the terrifying silent force of gravity. Long before the planet felt the first searing kiss of its star's heat, its fate was sealed by an invisible boundary in space. This line, known to science as the Roche limit, is not a wall but a precipice. On one side, a planet's own gravity is sufficient to hold it together, a cohesive sphere of rock and metal bound by its own mass. On the other side, the star's gravitational pull becomes a weapon. It is a differential force, a cosmic rack that pulls harder on the near side of the planet than it does on the far side. Imagine the world you're on now suddenly subjected to such a strain. The very ground beneath your feet would be tugged away from the core while the opposite side of the planet lagged behind. The world begins to stretch to deform. Its perfect sphericity, the hallmark of a healthy planet, is the first casualty. It elongates, becoming a grotesque egg shape, pointed accusingly at its destroyer. For the planet orbiting ZTF SLRN 2020, this was not a theoretical exercise. It was a physical reality playing out over its final agonizing orbits. We can envision the process unfolding in a slow, brutal ballet. The initial warping would have been subtle, detectable only by the most sensitive instruments. But as its decaying orbit dragged it ever closer, the stretching would have become catastrophic. The planet's crust, once a stable shell, would have groaned under the unimaginable tension. Great planet-spanning fractures would have ripped across its surface, releasing the tremendous pressure from its molten interior. Think of the most violent earthquake, the most explosive volcanic eruption on Earth, and then multiply that energy a millionfold. Geysers of magma, the very lifeblood of the planet, would have burst forth into the vacuum of space, not from isolated volcanoes, but from immense gaping wounds in the world's own skin. This is the moment a planet begins to die from the inside out. Its own internal cohesion, the force that held it together for billions of years, becomes its enemy. Every mountain range, every tectonic plate, every dense metallic layer of its core is now fighting a losing war against the star's inexorable gravitational gradient. The planet is being kneaded like dough, its internal structure failing catastrophically. It is no longer a single solid body. It is becoming a collection of massive gravitationally bound fragments, a flying rubble pile still loosely clinging to the shape of the world it once was. Its own gravity, the anchor of its existence, has been defeated. The star's tidal forces have won. The world has been tenderized, prepared for the main course of its own destruction, a celestial autopsy performed by the star's own immense mass. The planet as a cohesive entity has ceased to exist even before it truly begins to burn. Its solid form dissolves into a stream of cosmic debris. And with the structural integrity gone, the planet becomes vulnerable to the second wave of the assault. As this elongated, fractured ghost of a world spiraled closer, it entered the star's extended atmosphere. The corona, a region of tenuous superheated plasma, millions of degrees hot. Here the destruction transitions from a gravitational grind to a thermal inferno. The planet's own atmosphere, the delicate gaseous veil that may have once supported clouds winds and perhaps even the chemistry of life, is the next to go. It is subjected to a celestial blowtorch, a relentless stream of radiation and charged particles from the star. This stellar wind, a constant outflow from any active star, becomes a scouring blast at this proximity. It acts like a cosmic sandblaster, peeling away the atmosphere, layer by layer, stripping it from the unravelling planetary core with unimaginable violence. This is the process that left such a clear fingerprint in the data from ZTF SLRN 2020. When astronomers saw the sudden anomalous appearance of elements like sodium and calcium in the star's light, they were not just seeing a change in the star, they were witnessing the planet's final exhalation. They were seeing its atmosphere superheated into a glowing plasma being absorbed and incinerated. Each element burned with its own unique spectral signature, a barcode of its origin, a final fleeting message from the dying world. It's a haunting realization the light that travelled across the cosmos to reach our telescopes contained the chemical ghost of that planet's sky. We were in essence analysing the fossilised remnants of a planetary breath vaporised and woven into the fire of its own sun. This atmospheric stripping would have created a spectacular, if horrifying, vision. A vast glowing tail of plasma would have flowed from the planet, a comet of its own demise, its substance being siphoned away into the star's gravitational whirlpool. It was the world's soul, its gaseous essence being offered up to the furnace before its body was even consumed. With its atmosphere gone and its body shattered into a cascade of orbiting fragments, the planet enters the final irrevocable stage of its plunge. The remnants no longer follow a single clean orbit. They form a chaotic, swirling disk of material around the star's equator, a maelstrom of superheated rock-molten iron and vaporized silicates. This is the accretion disk, a temporary and violent structure born from the planet's corpse. Here, the friction between the countless colliding pieces of debris generates immense heat, causing the material to glow with incandescent fury. It is a funeral pyre the size of a solar system. From our distant vantage point, this glowing disk is what produced the dramatic and sustained brightening of the star, the flare that first signaled something extraordinary was happening. The star wasn't just exploding, it was feeding. It was drawing the remnants of its child into its own searing embrace. We must visualize this final act not as a simple fall, but as a cosmic waterfall. A river of planetary matter miles wide and thousands of miles long, spiraling down from the accretion disk and crashing onto the star's surface, the photosphere. The energy released by this impact is colossal. Each fragment, whether the size of a continent or a mere pebble, strikes the star's dense plasma at incredible speeds, converting its kinetic energy into a brilliant flash of light and heat. It is this continuous bombardment, this rain of planetary fire, that caused the star to swell and brighten for months. The star was in a very real sense suffering from a kind of cosmic indigestion. The light curve we observed was the chronicle of this celestial feast, a blow-by-blow account of a star consuming its own creation. The planet, which took billions of years to form, was unmade and absorbed in a matter of months, its substance raining down to become just another indistinguishable part of the stellar furnace. The cycle was complete. The material born from the star, forged into a world, had returned home. Yet the star does not emerge from this encounter unchanged. A meal this large leaves its mark. The sudden influx of heavier elements from the planet, lithium ion silicon, all the building blocks of a terrestrial world dramatically, if temporarily, alters the chemical composition of the star's outer layers. A star like ZTF, SLRN 2020, is primarily hydrogen and helium. The sudden appearance of these planetary metals is like a dye dropped into a clean body of water. It pollutes the star's pristine photosphere, creating a chemical imbalance that can persist for thousands of years. This metal pollution is the smoking gun for forensic astronomers. By analysing the star's spectrum long after the event, we can identify these foreign elements and confirm that the star has indeed consumed one of its planets. The victim leaves its own indelible fingerprint upon its killer, a final act of testimony written in the language of atomic physics. This infusion of new material does more than just change the star's chemistry. It can also stir its interior, disrupting the delicate balance of its magnetic fields. The accretion of planetary matter can trigger a period of intense magnetic activity, causing an outbreak of star spots, flares, and coronal mass ejections. The star becomes agitated, its surface roiling with the energy of its recent meal. In a strange vampiric sense, the star is rejuvenated. The angular momentum from the spiraling planet can even cause the star to spin slightly faster, a gravitational gyroscope given a final desperate push. The star, for a brief cosmic moment, is reborn more active, more volatile, and forever altered by the world it devoured. But this violent rebirth sends shock waves, both literal and figurative, through the rest of its solar system. The destruction of one planet is rarely an isolated event. Every body in a solar system is locked in a delicate gravitational dance with every other. Removing a planet, especially one as massive as a gas giant, is like pulling a critical gear from a finely tuned clock. The entire mechanism is thrown into chaos. For any surviving planets in the system of ZTF SLRN 220, the cataclysm is a profound existential threat. Their own orbits, once stable and predictable for eons, may now be fundamentally destabilized. They could be nudged into new, more eccentric paths, some being flung outwards into the cold darkness of interstellar space, becoming rogue worlds destined to wander the galaxy alone. Others might be pushed inwards, their own orbits now decaying, placing them on the very same downward path as their fallen sibling, their own fiery demise now merely a matter of time. This single observed event forces us to re-evaluate our entire model of planetary survival. We often imagine solar systems as peaceful clockwork places where planets follow their designated paths for eternity. But the 4K footage of this stellar engulfment paints a far more brutal and dynamic picture. It reveals that solar systems are not static museums. They're active, evolving ecosystems where life and death play out on a planetary scale. It suggests that planetary migration, orbital instability, and stellar cannibalism are not rare freak occurrences, but fundamental, and perhaps even common chapters in the life stories of stars. The survival of the fittest is a law that applies not just to life on a planet, but to the planets themselves. A world's continued existence is not guaranteed. It is a privileged one that can be revoked by the very star that gives it light and warmth. And so, we are left staring into the aftermath of a crime scene that spans millions of miles and billions of years. We have followed the evidence from the first subtle gravitational strain to the final fiery accretion. We have reconstructed the death of a world. But this single horrifying event opens a door to a much larger, more profound question. If it can happen there around a star so much like our own Sun in its final stages, how many other solar systems across our galaxy are currently poised on the brink of a similar fate? How many worlds that we are just now discovering are already on a downward path, their destruction preordained by the cold, unforgiving laws of celestial mechanics? We have solved the mystery of one star's meal, but in doing so we have uncovered a far deeper and more unsettling truth about the violent potential lurking at the heart of every star system, including one day our own. The universe is not just a place of creation, it is a place of consumption. And so the light from that final terrible spectacle reaches us across the void. What you have just witnessed is more than an ending. It is a Rosetta Stone written in fire and gravity delivered from the depths of space and time. For decades, the demise of worlds like this was a story told only by mathematics, a silent film playing out on supercomputers in sterile climate-controlled rooms. We could sketch the theory, outline the grim choreography, but we were always on the outside, looking and separated by an impassable gulf of scale and probability. We had only the cold ashes, the circumstantial evidence of stars mysteriously polluted with heavy elements. But now, with this data flowing through our telescopes, we have a confession. We have the star, the victim, and the weapon all captured in a single unprecedented act of cosmic testimony. The silence has been broken, and the story it tells is rewriting everything we thought we knew about the life and death of solar systems. The very first transmission we decoded from the event was not an image, but a ghost. It arrived as a spectrum of light, a precise barcode of the star's atmosphere that our instruments dissected photon by photon. Before the cataclysm, this star's chemical signature was predictable, a simple hydrogen and helium song it had been singing for billions of years. But in the hours and days following the planet's final plunge, the star's song changed. It became a chorus, then a shriek, as new and alien notes were violently added to the composition. Suddenly, the star's light was screaming with lithium, a fragile element that should have been burned away in the star's infancy. Its presence was a flag planted in the stellar surface, a clear sign of freshly delivered undigested material. Then came the undeniable signatures of rock and metal. There, glowing in the star's churning plasma, was silicon, the fundamental constituent of sand and stone. We detected magnesium, a key component of planetary mantles, and aluminum, forged in the hearts of previous long-dead giant stars. And most profoundly, we saw the unmistakable spectral lines of iron, the heavy heart of a terrestrial world now smeared across the face of its executioner. This was not a subtle hint or a vague suggestion. It was a planetary autopsy performed at a distance of hundreds of light years. Each spectral line was a fragment of a lost world, a chemical echo of continents, oceans, and a molten core that once generated a magnetic field, a world that once traced a serene and stable path through the darkness. For the first time, we are not just inferring that a planet was consumed. We are reading its elemental recipe, cataloguing the very ingredients that a long-extinguished star once cooked and bequeathed to this system, ingredients that coalesced into a world, only to be returned to a star in a final fiery sacrifice. This chemical fingerprint does something remarkable. It transforms our understanding from theoretical to tangible. We can now compare the exact abundance of these elements in the star's atmosphere to the predicted composition of the planet based on its size and density, which we had measured years before. The numbers miraculously align. The amount of iron we now see contaminating the star is consistent with the mass of a core we calculated for a planet of that specific size. The ratios of silicon to magnesium perfectly match the models of rocky world formation. It's like finding a shipwreck on the ocean floor and then discovering the captain's log perfectly preserved, detailing the ship's cargo down to the last crate. This one-to-one confirmation is a breakthrough of monumental importance. It provides a benchmark, a point of absolute truth against which all our theories of planetary composition can now be measured. When we look at distant exoplanets from now on, our models of their internal structure, of their potential to be Earth-like, will be sharper and more confident, all because we watched one of their kind die. But the revelations did not stop with a chemical inventory. The sheer resolution of our observations, the ability to watch this celestial train wreck frame by frame, has given us an unparalleled lesson in the physics of annihilation. We watched the planet's orbit decay not in a smooth, elegant spiral, but in a chaotic, lurching stagger. For years our models depicted this process as a stately, almost gentle gravitational dance, a slow surrender to the inevitable. What we saw was a brawl. The star, bloated and unstable in its old age, was not a perfect sphere. Its gravitational field was a lumpy, unpredictable mess, and its surface roiled with colossal magnetic storms. These imperfections grabbed hold of the doomed world, yanking and twisting it, accelerating its descent in ways our simpler models had never anticipated. The planet itself fought back. As it was pulled closer, its own gravity warped the surface of the star-raising stellar tides of incandescent plasma thousands of miles high. This exchange of energy, this gravitational wrestling match, created feedback loops that were astonishingly violent. We could see the planet flexing its very crust, cracking under the strain. We witnessed what must have been unfathomable earthquakes and volcanic eruptions on a world being torn limb from limb, all before it ever touched the star. This is the new chapter we must now write in the textbooks of orbital dynamics. The end is not a simple fall, it is a complex, brutal and interactive struggle. The data we've collected on these tidal forces, this intricate gravitational dialogue between a star and its planet in its final moments, is a treasure trove for theorists. They are now recalibrating their simulations, adding new layers of physics to account for the beautiful, terrible chaos we saw unfold. Our predictions for the fates of other worlds have just made a quantum leap in accuracy. We can now look at another solar system, one with a Jupiter-sized planet, orbiting perilously close to its aging star, and we can model its future with an authority we never had before. We can account for the star's magnetic activity, for the subtle wobbles in its rotation, for the precise gravitational harmonics that will either grant the planet a stay of execution or seal its fate. We have moved from celestial fortune-telling to genuine forensic forecasting. For thousands of known exoplanets, their long-term horoscopes have just been dramatically rewritten. We can now triage entire solar systems, identifying which worlds are coasting in safety for billions of years and which are already feeling the first faint tidal pull of their own star's deadly embrace. You are living in the first moment of this new era, the moment we stopped being passive observers of the cosmos and started becoming true diagnosticians of its future. This single observation, this one star's meal, acts as a cosmic anchor, a fixed point of reality in a sea of abstract theory. Every computer model of stellar evolution, of planetary formation, of galactic dynamics is a magnificent but ultimately incomplete human creation. These models are filled with assumptions and approximations, variables that we have to estimate because we've never had the data to nail them down. We have parameters for how efficiently a star mixes material in its convective zones, for how planetary orbits migrate over eons, for the precise melting point of planetary cores under extreme pressure. For decades, these have been educated guesses, but now we have the answer key. The light curves, the spectral data, the gravitational perturbations we recorded from this event, this is ground truth. It is a torrent of hard data that astronomers are now using to lock down those free-floating variables. They are plugging this event into their grand simulations, and for the first time the models are snapping into focus, the blurry edges becoming sharp. It's like tuning a grand piano that has been out of key for centuries. Suddenly the music it plays, the music of the cosmos, sounds clearer, more resonant, more true. This calibration will ripple outwards through nearly every field of astronomy. When we try to understand how planetary systems form our models, we'll now be seeded with more accurate initial conditions. When we hunt for Earth-like worlds, our analysis of their potential stability will be far more robust. Even our understanding of our own solar system's distant future, when our sun begins to swell 5 billion years from now, has been profoundly refined by the death of this one distant anonymous world. And it is here in the synthesis of all this new knowledge that we find the most breathtaking revelation of all. We have been watching an act of utter destruction, the complete and total erasure of a planet. It is a vision of endings of cosmic nihilism. And yet, if you look closely enough, if you follow the journey of matter and energy to its ultimate conclusion, you realize that we have not been watching a death. We have been watching a rebirth. The elements of that vaporized world, the iron from its core, the silicon from its mantle, are not destroyed. They have been bequeathed to the star. For the next few million years, they will swirl within its fiery atmosphere a temporary enrichment, a fleeting memory of the planet that was. But the star too is mortal. As it continues to age, it will shed its outer layers. In a final glorious puff, it will cast off its atmosphere into space, creating a magnificent structure known as a planetary nebula. And carried within that expanding cloud of gas and dust will be the ghost of the consumed planet. The iron, the magnesium, the silicon will be scattered into the interstellar medium, enriching it, seeding it with the raw materials for the next generation. This stellar debris, this cosmic shrapnel, will drift for eons through the galactic night. Eventually, gravity will pull it together with other clouds of gas and dust remnants of other dead stars. A new stellar nursery will form a crucible of creation, where the ashes of the old are forged into the new. Out of that collapsing cloud, a new star will ignite, and encircling it, a new disk of protoplanetary material will swirl thicker and richer in heavy elements than the one before it. And within that disk, the very same iron atoms that once constituted the core of the world we just saw die will begin to clump together again. They will form planetesimals, then protoplanets, and perhaps, just perhaps, a new rocky world will take shape. A second-generation Earth built from the recycled remains of its long-lost ancestor. This is the universe's most profound secret. Nothing is ever truly lost. Creation and annihilation are not opposites. They are two parts of the same eternal cycle, a cosmic engine of renewal that churns matter and energy through stars and planets, through life and death, across unimaginable spans of time. You have seen a world end, but what you have truly witnessed is the first step in the creation of a world yet to come. A single violent act in one corner of the sky has illuminated the grand narrative of our galaxy, the majestic interconnected story of how the universe builds, destroys, and builds again. It is a story in which every ending is just a new beginning in disguise, and so the spectacle fades. The light from that final, desperate flare of a dying world, having travelled across unimaginable gulfs of space and time, has now passed us by. What remains is the afterglow not just in the telescope's sensors, but in our own minds, an indelible image burned into our collective consciousness. For generations, the idea of a star consuming its own children was a ghost story, told through the language of physics, a chilling prediction whispered by lines of code and complex equations. It was an abstraction, a celestial what if, confined to the sterile pages of scientific journals and the vivid imaginations of artists. We had seen the theoretical blueprints, the gravitational arguments, the statistical likelihoods, but we had never truly borne witness, not like this. The journey to this moment was a testament to human persistence, a multi-generational quest for a glimpse of the inevitable. We followed the subtle clues, the faint rhythmic dimming of a distant star suggesting something was amiss in its system, the telltale spectral fingerprints of polluted starlight, hinting at a celestial crime scene contaminated with the elements of rock and metal that should never have been there. These were the faint tracks in the cosmic dust, the scattered pieces of a puzzle billions of years old. We built observatories that acted as colossal funnels for ancient light-designing instruments of breathtaking sensitivity, all in the hope of catching a monster in the act. And then it happened. The ghost stepped out of the shadows and into the stark, unforgiving clarity of our most advanced instruments. What we captured was more than just data. It was a cosmic autopsy report written in light and delivered in ultra-high definition. That string of images, that 4K footage of a world's demise transformed everything. It took the abstract and made it visceral, undeniable, and profoundly real. We saw the planet once a sphere of rock and ice, warped by the star's immense gravity, its very shape distorted into a teardrop of incandescent matter. We watched its atmosphere being siphoned away, a shimmering ethereal plume feeding the very star that gave it life. We witnessed the final catastrophic disintegration, not as a single distant flash, but as a detailed moment-by-moment chronicle of planetary death. In those frames, we saw the geology of another world, its core, its mantle, its crust unmade before our very eyes, its elemental signature flaring brightly for one last defiant instant before being swallowed by the stellar furnace. There is no longer room for debate or skepticism. We have now read a eulogy for a planet we never knew, and in doing so we have confirmed a fundamental, terrifying, and strangely beautiful truth about the universe we inhabit. This truth forces us to re-evaluate our understanding of the cosmos, not as a serene clockwork mechanism, but as a living, breathing, and profoundly violent ecosystem. For so long we have viewed events like this through the lens of catastrophe, as cosmic accidents or tragic finales. But the evidence we have painstakingly gathered, culminating in this single breathtaking observation, suggests a different story. It suggests that this is not an anomaly. This is business as usual. The universe, it seems, is not sentimental. It operates on principles of recycling and renewal that are as relentless as they are impartial. The destruction of a world is not merely an ending, it is a vital part of a much grander, more intricate cycle. It is a form of celestial metabolism. Think of the elements that made up that doomed planet. The silicon in its rocky mantle, the iron and nickel in its core, the carbon and oxygen locked in its frozen gases. These were not created in the Big Bang. They were forged long ago in the hearts of stars even more ancient than the one we just watched. They were scattered across space in the fiery death of a supernova drifted for eons as cold, lonely atoms in the interstellar darkness, and then drawn together by gravity they found a new purpose. They coalesced into a new star and a new family of planets, including the one whose final moments we just chronicled. That planet was in essence made of stardust, of the recycled remnants of a previous cosmic generation. And now its own story has come full circle. As its matter was pulled into its parent star, those very same elements, silicon, iron, carbon, did not vanish. They were plunged back into a nuclear forge. Within the star's churning convective layers, they are now being subjected to immense heat and pressure, their atomic structures reconfigured. The star itself is enriched, its chemical composition fundamentally altered by the meal it just consumed. For the remainder of its life, it will bear the chemical ghost of its lost child. And when this star too finally reaches the end of its own life, whether in a gentle exhalation, as a planetary nebula, or a far more violent explosion, it will cast these enriched materials back out into the void. The atoms of that devoured world, now twice processed through the crucibles of stellar cores, will once again be scattered among the stars. They will become the raw ingredients for the next generation of solar systems, the building blocks for new planets, new moons, and perhaps somewhere in the distant future new life. From this perspective, the act of destruction becomes an act of creation. It is the universe's grand patient alchemy turning worlds into starlight, and starlight back into worlds. The galaxy is not just a collection of static objects. It is a dynamic system that feeds on its own creations to perpetuate itself. Each planetary engulfment is a deposit into a vast cosmic bank, an investment in the future. The very ground beneath our feet is composed of atoms that have likely undergone this exact same cycle multiple times over the last 13 billion years. The iron in your blood, the calcium in your bones, they are the ashes of dead stars and quite possibly the vaporized remnants of long-forgotten planets. We are all of us living proof that the universe rebuilds itself from its own ruins. This spectacular act of destruction we witnessed was not a funeral. It was a harrowing but necessary link in the infinite chain of cosmic rebirth. And yet our role is not simply to be passive observers of this majestic process. The capture of this event in such astonishing detail is a watershed moment, not just for what it taught us about the universe, but for what it tells us about ourselves and our capabilities. This was more than a lucky shot in the dark. It was the dawn of a new era in astronomy, the era of dynamic observation. For centuries, astronomy has been a science of snapshots of static images of galaxies and nebulae that change on timescales far too long for any human to perceive. We were like photographers trying to understand a raging river by taking a single frozen picture of one droplet. But now that is changing. With telescopes powerful enough to capture events in high resolution in near real time, we are becoming cosmic cinematographers. We are beginning to see the universe for what it is, not a static portrait, but a dynamic, evolving film filled with action, drama, and constant transformation. This 4K capture is the proof of concept. It is the technological and methodological foundation upon which the next generation of discovery will be built. On the mountain peaks of Chile, the extremely large telescope is rising its primary mirror so vast it will gather more light than all previous professional telescopes combined. In space, the Nancy Grace Roman Space Telescope is preparing to survey the sky with a field of view 100 times larger than Hubble's, allowing it to monitor millions of stars simultaneously for the telltale signs of planetary feasts. These instruments and others like them are designed specifically for this new kind of science. They won't just find more examples of stars eating planets. They will allow us to study the process with a fidelity that was once the exclusive domain of science fiction. We will be able to watch the entire process unfold from beginning to end. We'll measure the precise gravitational tides that stretch a planet apart, providing a direct test of our theories of gravity in extreme environments. We will use spectroscopy to analyze the chemical composition of a planet's atmosphere, as it is stripped away layer by layer, giving us an unprecedented look at the atmospheric structure of an alien world. We will even be able to detect the shock waves and magnetic reconnections that ripple through a star's corona as it ingests a massive object, learning more about the complex physics of stars themselves. We have seen one star eat one planet, but in the coming decades we will build a comprehensive catalogue of these events across a vast range of star types and planet sizes. We will move from witnessing a single shocking event to understanding the complete statistical demographics of planetary survival and destruction across our entire galaxy. We're standing at the threshold of being able to watch the cosmic ecosystem in motion. This new capability, however, brings with it a profound and deeply unsettling paradox. At the very same time that we are refining our ability to watch worlds die, we are pouring immense resources into the search for life on worlds elsewhere. The two pursuits are inextricably linked. Our search for habitable exoplanets for Earth 2.0s, orbiting in the gentle warmth of their stars, is driven by one of humanity's most ancient questions: are we alone? We scan the heavens for the subtle signatures of water, of oxygen, of methane, the chemical hints of a biosphere. We dream of finding a pale blue dot like our own, a world teeming with the possibility of life. But this recent observation serves as a stark and chilling reminder for every world that might be a cradle for life. There are countless others that are destined for the grave. The galaxy, it turns out, is a minefield. The very processes of stellar evolution that create the conditions for life also inevitably create the conditions for its annihilation. A planet might spend billions of years in the stable, life-giving habitable zone, only to have its orbit destabilized by a passing star or a gravitational nudge from a larger sibling planet sending it spiraling into its sun. Even if it avoids that fate, its own star is a ticking clock. As we have seen, the transformation into a red giant is a guaranteed death sentence for any inner planets. So how does this knowledge, this visceral 4K confirmation of how common planetary destruction might be, reframe our search for life? It adds a new critical variable to the Drake equation, the famous formula used to estimate the number of intelligent civilizations in our galaxy. We must now account not just for the number of planets that form in the right place, but for the number of planets that survive long enough for complex life to evolve. The cosmic graveyards are likely far more full than the cosmic nurseries. This might offer a partial and rather grim solution to the Fermi paradox, the question of why in such a vast universe we have not yet found any evidence of other intelligent life. Perhaps civilizations are routinely snuffed out by these predictable stellar cataclysms before they ever have a chance to reach across the stars. Perhaps life is not a hardy weed growing in every available crack, but an incredibly fragile flame, a fleeting candle flickering in the face of a cosmic hurricane, easily extinguished by the indifferent mechanics of the universe. This realization does not mean we should abandon the search. On the contrary, it makes the quest even more urgent and any potential discovery infinitely more precious. It imbues our search with a sense of profound responsibility. If we do find life elsewhere, we will know just how lucky it was to have survived. And if we find that we are after all alone, it underscores the monumental, terrifying and sacred rarity of our own existence. We would be the sole witnesses to this grand cosmic drama, the only known consciousness in a galaxy of silent, beautiful machinery. The knowledge that worlds are born and worlds are destroyed makes our own world and our own consciousness all the more miraculous, and so, inevitably, we must turn our gaze back home. It is impossible to witness such a vivid depiction of a planet's end without contemplating the ultimate fate of our own. That distant star, now swollen and red, consuming its child in a final fiery embrace, is not an alien monster. It is a ghost of Christmas future. It is a direct preview of what will happen right here in our own solar system. Our sun, the source of all life and warmth on Earth, is not eternal. It is a star, and it too is aging. It has been burning steadily for 4.5 billion years, but its fuel is finite. The process that will one day lead to Earth's destruction has already begun. Right now, the sun is fusing hydrogen into helium in its core, but as that hydrogen runs low, the core will begin to contract and heat up. This will cause the sun's outer layers to expand dramatically. This isn't a distant abstract event. In about 1 billion years, the sun will have grown bright enough to boil Earth's oceans away. Our world will become a searing, sterile desert, its atmosphere stripped, its life extinguished. The long, beautiful story of life on Earth will be over, but the planet itself will still be here, a scorched, silent rock continuing its lonely orbit. For a time, a few billion years after that, the final act will begin. The sun, having exhausted its core hydrogen, will swell into a true red giant. Its outer edge, a wall of incandescent plasma, will expand relentlessly outwards. It will swallow Mercury first, vaporizing the tiny planet in an instant. Then it will consume Venus, dissolving our sister world into the stellar fire, and then its gaze will fall upon Earth, our planet, the only home we have ever known, the stage for all of human history, for all of evolution, for every act of love and war, discovery and despair will be engulfed. The rock and iron of our world will melt, then boil, then dissipate into the sun's atmosphere, becoming just another trace element in its vast burning mass. Our planet will cease to exist. The third rock from the sun will be nothing more than a memory, and there will be no one left to remember it. This is not a possibility. It is a certainty written into the laws of physics. It is the destiny of our world. And yet this knowledge should not inspire despair. It should inspire a sense of profound awe and deep perspective. We are living in a privileged moment, a fleeting window of cosmic time when our planet is habitable. Our star is stable, and we have developed the consciousness to understand it all. We are the universe made aware, the lucky inhabitants of a temporary paradise. The spectacle of that distant planet's death is not just a warning, it is a gift. It is a cosmic memento mori, a reminder to cherish the here and now, to appreciate the incredible fragile miracle of our existence on this pale blue dot. It reminds us that we are not separate from the universe, but an integral temporary part of its majestic, unending cycle of creation, destruction, and renewal. Our journey to understand the stars has led us, as it always does, right back to ourselves and to our own precious fleeting place in the cosmos.